Okay, welcome back. We are now going to do what I think is the more difficult equivalence to generate or to verify, and that is the equivalence between regular expressions and non-deterministic finite automata. Let's go. I think my notes are better for this, so I think this will go more smoothly. And also, I think you should follow this lecture instead of reading the book, because the book has an error, which, though extremely subtle, is in fact disastrous, and it's just wrong. Okay, let's go. We want to now, what are we trying to do? We are trying, given an arbitrary regular expression, to create a machine which accepts precisely the strings that this regular expression matches. Okay, and the flexibility with regular expressions is that they have been defined recursively to be composed of the operations of concatenation, alternation, and the Kleene star. Still haven't looked up how to say that guy's name. So, any algorithm we present to do this is going to itself have to be recursive. Let's go. Let's go. Okay, so first of all, we will deal with the base cases. Okay, so what are the base cases? Well, it's easy to forget this because it's sort of part of our technical definition of regular expressions. But there were some base cases for regular expressions. In particular, the empty set is itself a regular expression. Okay, so great, kind of a boring regular expression. It matches nothing. What I would now like to do is to present a machine which accepts precisely the strings that this regular expression matches. Okay, I'm going to introduce this sort of blue arrow to represent the meta-linguistic notion of this regular expression is captured by the following machine. And okay, what is a machine which accepts no strings? Well, it's just the machine with one state, it's the start state, and it is not an accept state, and there are no transitions. So when this machine tries to read any string, it just immediately dies. And this is an NFA, and I think this works. Okay, what about lambda, which is the null string? Well, the null string is a string, and there is one, or rather I should say, this regular expression is matched by one and only one string, that is the null string. So how do we make a machine which accepts the null string and no other strings? Well, I think it's easily done. We just have a start state, we make it an accept state, and that's it. It accepts immediately, but any subsequent characters die. Okay, and that's pretty silly. But okay, also, what's the other sort of base case for regular expressions are if you just have a single character. And this is a regular expression, and what matches this regular expression? Well, only strings which are of length 1 and consist of the character A. And so, let's write a machine which accepts only the string of length 1 consisting of just the character A. I think that's kind of easy to do. You have a start state, which should not be an accept state, because we don't want to accept the empty string, the null string. And then, upon reading an A, we should go to some final state, and in that final state, we accept. And the lack of transitions out of this state means any subsequent characters we read die. Okay, so this is the base case. That was kind of maybe a little bit silly or something. Okay, now I shall introduce the. I will now sort of proceed to the inductive case. So the inductive cases. Well, I need to show you how, given more complicated regular expressions, we can create, which have already machines associated with them. We can create a new machine to recognize the combinations of those regular expressions. So, what I would like you to now do is suppose, and this is so torturous to be doing on a small whiteboard, But let's suppose that I have some regular expression x. Okay, and here I use like yet another kind of variable. This capital X represents, you know, some perhaps more complicated regular expression. Let's suppose that it has been adequately captured or represented by machine AX. And suppose I have some regular expression y. Again, y is a variable which refers to a perhaps quite long regular expression. And let's suppose that it is represented by a sub y. So machine a sub y. Ax and ay are machines. Okay, and what I'm now going to explain is how to create the xy machine, the x or y machine, and the x star machine. Okay, so first, what does a kind of a generic machine look like? Well, the recursive presentation of this algorithm is effective because every regular expression is itself defined recursively from these set of base cases and the three operations which create larger regular expressions out of smaller regular expressions. One thing that x and y might be are, you know, the base cases, but otherwise, you know, there's something bigger. Okay, so when I sort of think of what this machine looks like, I have to imagine that it has it's a machine, so it has a start state, it has a set of accept states, it has a bunch of transitions, and so, okay, a generic picture of this machine looks like this. Let's see, and then, so there's a start state. Let little s sub x, let that be the start state of machine a sub x. And then it's going to have some transitions. I don't want to draw them because the idea is that we're sort of abstracting away from any particular machine. I want this algorithm to work in general. And well, this machine is going to have one or more accept states. So let's let fx1 and fx2, for example, be some accept states of this machine AX. And okay, there's one more thing we have to sort of worry about a little bit, which is that it's of course possible for the start state of machine AX to be itself an accept state. So what we're going to do now is put like a dotted concentric circle here to indicate that this start state may or may not be one of the accept states of the machine. Okay, and now maybe like in red or something, I'll draw kind of like a bubble around what I have written to indicate that we should think of that red machine as a sort of a generic representation of kind of an arbitrary machine, a sub x. And let's just do the same thing for a sub y. So what does a sub y look like generically? Well, there is a start state, s sub y, which may or may not be an accept state. And it's going to have, you know, transitions out of it, you know, blah, blah, blah. And it's going to have fy1 and fy2. Okay, of course, there's nothing, you know, there's nothing special about there being two accept states. There could be any number of accept states, or one or none. But there, you know, there may be, you know, more than one. So I'm just drawing two. And now I will put kind of a green bubble around this machine to indicate that once again we're not going to look at its internal structure. And so in fact, the algorithm which I am presenting is going to explain how to convert one of these more complicated regular expressions to a machine, and the only thing I really need access to is the set of, or the start state and the set of accept states for the machines which I'm assuming already exist by virtue of the recursion. Hope I'm explaining this well. Good. And built into the very definition of a machine is what the start state is and what the accept states are. So if we assume by recursion that these machines have been constructed already at a previous step, then we certainly have access to those steps, to those states. Okay. Good. Well, this is all the suppose, which is to say, in words, suppose that we have regular expressions x and y, which have been represented by machines a sub x and a sub y. What must we do in the recursive step now of the presentation of this algorithm? I have to tell you how to create machine xy, how to create machine x or y, I'll just pronounce it like that, and how to create machine x star. Okay, and if I can do this, then since every regular expression is composed of these three characters and then an arbitrary number of applications of these three rules for creating larger regular expressions, then I have now accounted for all regular expressions. This is a kind of it's sort of a something which is sort of very common when dealing with formal languages, and in fact in logic, which is it's a kind of a, well, it's basically like a proof by induction, but it's a proof by induction in disguise. It's a proof by induction on the length of the formula. So in this case, on the length of the regular expression. My real claim here, not to get too caught up in the details, but my real claim here is that all regular expressions have a corresponding machine associated with them. So how do I prove that that's true for all regular expressions? Well, I do it by induction on the length of the formula. And not actually induction by the length of the formula, but on the sort of length of the number, or on the number of sort of applications of the processes for creating larger regular expressions out of smaller regular expressions. But normally people don't think of it really as a proof by induction. They just sort of think of it as a kind of recursive proof. I show the effectiveness of the algorithm for the base cases. I show the effectiveness of the algorithm for the inductive cases of the inductive definition of regular expressions, and then we call it a day. Okay, this is too much talking. Let's do it. Well, after all this setup, I think it's just going to be really obvious what to do. What is ultimately regular expression xy? Well, it's a new regular expression, which is the concatenation of this regular expression and this regular expression. So what is xy going to match? Well, it's going to match any string composed of a substring, which matches regular expression x, immediately followed by a substring which matches regular expression y. And so, if I have a machine which will accept any string which matches regular expression x, and I have a machine y which matches any string which which accepts any string which matches which matches regular expression y, then I kind of just have to put the machines back to each other. In order to be a string that gets through the machine, through the xy machine, you need to first sort of make it through the ax machine, and then immediately followed by that, you need to make it through the ay machine. Okay, and so algorithm sort of by picture here. What are we going to do? It's a little bit complicated, but so I have the kind of ax machine, and it looks like this. So that's x. La 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 la, and then we have the do, and then it's got its various things, and then we have these various fx1. F. I guess there's like multiple subscripts going on here. Yeah, fx1 and fx2, and those are accept states, and etc. etc. Okay, so that's my machine x. I'm just sort of redrawing it now. And then I have this machine y, which has a start state, which once again might be an accept state, and then it has, you know, transitions of drawing here, and here's Fy1 and here's Fy2. These are the accept states of machine AY. Okay, and I'm going to just now tell you precisely how to create the AXY machine. And okay, if we were doing this live in class, you would just all spontaneously tell me what to do, because I think it is intuitively clear that first of all, the start state of the AXY machine should just be the start state of the X machine. And so I put sort of, maybe I put a red arrow or something like that there. Now, we have to be a little bit careful, because, all right, sort of almost immediately we find ourselves in this strange situation where, suppose, and this is why Gossett and I are emphasizing this with this sort of dotted concentric circle, that the start state of machine X, the machine AX, is an accept state. Well, that should not be an accept state, generally speaking, of our AXY machine, of course, because it's not enough. If the null string matches regular expression X, that doesn't mean that the null string will match a regular expression XY necessarily. And so, because we have to make it through the Y machine too. So if we have to make it through the Y machine too, then what I need to do is kind of remove, and hereby I do this now, so algorithm by explanation of me erasing things with my fingers, you have to remove the accept state status from the start state of machine AX, if it was indeed one. And I'll just do that for all of these, right? For all of the accept states, it's really, maybe it was simpler to start with the states that I know are accept states, fx1 and fx2. But really what I'm now going to do is to apply to every accept state of machine X. I need to say, well, you're not an accept state anymore. You made it through the first half of this string, so to speak. But in order for this string to be accepted by the AXY machine, it now needs to make it through Y. And so I think it's clear what to do. We are going to, I guess I'll do it in red, what we're going to do is to just lambda transition from the accept states of machine X to the start state of machine Y. Okay, so I hereby do the following. Assign the start state of machine XY to be the start state of machine X. Remove, of course, the start state status of machine Y. So we're sort of dissolving these two machines, so to speak, and creating a new machine out of them. And now, remove the accept state status from every accept state in machine X, and lambda transition from each accept state of machine X. And here I have to put like a dotted arrow to indicate the fact that I may be adding, so okay, these are, let me just finish. That's a lambda, and this lambda being, labeling this dotted line is indicating the fact that we add that if and only if the start state of machine X was an accept state. Okay, so basically, dude, you just get a free pass from the end of machine X to the beginning of machine Y. It's really that simple. And then, I think that's just it, right? Then we let the accept state of the accept states of the new machine AXY are going to be whatever the accept states of machine Y are. Okay, and so I will now put a kind of a blob around this, because in some ways I've completed the machine now. So I'm going to put the case back on, so to speak, and there it is. I've outlined how to take two arbitrary machines, and by fusing them together into a new machine, I've told you what the start state is of that new machine. I've told you what the accept states are of that new machine. and I've told you how to sort of glue the two machines together. And in this case, for concatenation, we do the obvious thing, which is to lambda from every except state of the X machine to the start state of the Y machine, and then that's it. And with the final, yeah, I think I said that already. Okay, that was kind of technical and maybe a little bit subtle, and you could have made perhaps an error in the details, but the general gist of what to do, I think, was kind of obvious. And it is equally obvious, I think. I've just changed my mind about spacing. I'm going to do this now. I think it is equally obvious how to handle the regular expression x or y. And basically, what does it take to match regular expression x or y? Well, you either need to match x or you need to match y. Therefore, if I have a machine ax and a machine ay, a machine which would accept a string matched by x or y should be a machine which, a new big machine, which either, for which you could either make it through the ax machine or the ay machine. And there is, via non-determinism, I think, a very clear way to do this. And that is, you just do both, right? You just lambda transition your way to both. So once again, suppose I had machine, let's see, suppose I had machine x, I had machine x, and this was the start state, and maybe it was an accept state, and then, blah blah, there's no faster way to do this. And then, so this is machine ax, and I shall also draw machine ay, and it's got its various things. Woo. And then it's got its various things, and then there's the two, although there's nothing special, like I said, about two, accept states of the ay machine. Okay, how can we create a new machine for, well, I might as well just call that new machine the A, X, or Y machine. Well, I think it's clear what to do. We create a new state, call it S, X, or Y. Let it be the start state. And now, simply lambda to the start states of the previous two machines. And so what I'm now going to do is I'm going to remove the start state status of Sx and Sy, of course, because a machine can only have one start state. Here it is. This is a new state that I've created in this construction. And now you just lambda to the start state of Sx, of machine Ax and machine Ay. That is, I believe, just it, right? And then the accept states of this machine are going to be the accept states of Ax and the accept states of machine Y. So I have just, once again, I've just showed you how to algorithmically create a new machine out of the two old machines. And I think it's clear, just from the construction, that the only way for a string to get accepted by this machine is for it to either be accepted by the X machine or the Y machine, sort of, or both. And if a string makes it through this machine, then it must have made it through the X and AX or machine or the AY machine. And so this construction captures this. Okay, so we'll now put the blue arrow. I've now represented X or Y. Okay, all of that was like pretty obvious, I think. Now comes the hard part, and maybe this is not worth spending time talking about things that are wrong, but Gossett's algorithm on page, I love to just attack this guy. It's like my mentor and my enemy, so I shall, I have to like destroy him or whatever for Yeah, I'll stop there for various reasons. Okay, so here I think this is more complicated, and what he did on page 564 is in fact just wrong. Okay, what should we do? Well, okay, what is x star? X star is a regular expression which matches 0 or more instances of something matched by x. And so the kind of idea is that to be accepted by the x star machine, we should be composed of some sort of like looped number of like x machines in some kind of way, right? So if you can make it through the x machine, say 5 times, where when you get to the end of the machine you start back up again from the beginning, then that means if you made it through the x machine 5 times, that your string matched, you know, x, 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 x. And if you match x, 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 then you match x star, because x star just asks that you be composed of 0 or more applications. Okay, and yet also, of course, the empty string, the null string, is going to match x star, so we have to sort of account for that. Okay, what do we do? Once again, I begin my algorithm with this machine Sx, or with this machine Ax, which looks like this, and has fx1, and I think here we do have to be, okay, whatever. Okay, and so good, and then there are things and blah blah. Okay, so how do I convert this machine into the x star machine? We do as follows. Create a new state. Call it Sx star. This is going to be the new start state of this overall machine. And owing to the fact that the null string matches x star, I'm going to make this an accept state automatically. Okay. Then remove the start state status of what was the start state at Ax. Of course, there can be only one start state per machine. And simply lambda from here to here. So, okay. And then, basically, when this machine, if we ever get to, make sure I say this correctly, yeah, if we ever get to, okay, yeah, and then basically, I'll just say it, then just lambda to any, lambda from each of the accept states of machine Ax to to what was the old start state of this machine. Okay, what is going on here? What's going on here is, we begin. It's a new created state. We sort of go out of our way to make that an accept state, because that handles, in kind of separately or something, the case in which the null string has now automatically been made to match, so it has automatically been made to be accepted by this machine, which is what it should be, because the null string matches x star. Okay, but now, what is x star? Well, x star is supposed to like, I'm just kind of repeating myself here, but you know, it matches any string which has like some number of x's. And so if you have some string which is has 3 x's, for example, back to back to back, and what I really mean by that is, suppose you have some string composed of 3 substrings, and each of those 3 strings matches x, matches regular expression x, which is itself a more complicated regular expression. Well then, does this machine accept that string? Well, yeah, it just does, right? Because we go here, we immediately lambda to what was the start state. Then, since this machine, by inductive hypothesis, matches, or this machine, what word have I been using, represents x, then the first substring, I said it was xxx, is going to sort of make it through and end in an accept state. But now, instead of accepting that string as is, we lambda back to, well, first of all, I should say that if the string one thing that x star should match is one thing that x star matches is just x, right? So if the string matches x, then that string should also match x star. So that's why we keep these as accept states, because now that string would just terminate here in the accept states of the original AX machine and would just be accepted. But if in fact the string is of the form xxx, then we would lambda back to the beginning and sort of run it all back again. And so however many times, if there are 3 times, say, or if the string that's matching x star is composed of 3 x's, then we sort of take 3 loops through this machine, each time processing one of those strings, and that's just it. And the sort of non-determinism allows us to sort of lambda from the final states, sort of or not, right? So on the last time when the string finishes processing, if we end in an accept state, then we just accept it. Okay, this is a lot of talking to just say, dude, here's your machine. And I put a green box around it, or a green blob around it once again, and I've now just presented, and I've sort of argued a little bit, maybe casually, that this machine does the job, that it represents, this machine, which I'm calling AX star, represents x star. Okay, and the one thing I'll say here is that this is I think the subtle part. This creation of a new machine and then a lambding back here. Gossett, incorrectly, though it's quite subtle, has us add lambda transitions from the accept states to this state. That is an error because that machine will accidentally, if you follow Gossett's algorithm, that machine could accidentally accept strings that it should not accept. Because if the start state of machine AX is an accept state, say, but it is also a state for which inside that machine other arrows kind of lead back to it, then we might find ourselves kind of mid-string or something like that, being in. This is too hard to explain. I think as I go over the homework, maybe I will give an example of doing this algorithm incorrectly following Gossett and show why it doesn't work. But I think it's clear to everyone that this works. Perhaps it's not clear why this is all necessary. Okay. Oh my God. Good. It seems like this video is about to end, and so I guess I'll just keep talking.